Prepare to experience the strongest radio allowable by law. Secrets will be revealed. Myths dispelled.
From the studio gym where excuses never apply.
It's Superhuman Radio with your host, Carl Lenore.
Hey, welcome back to another episode of Superhuman Radio. One of my favorite topics today, and has been for the past 13 years, is anti-aging. But, you know, when you talk about anti-aging to mainstream people, they immediately think of some sort of face cream that makes you look younger. When we talk about anti-aging, we're talking about mitigating or slowing age-related diseases, living longer, greater vitality, greater health span. Lifespan is not enough. If you spend the last 30 years of your life in a wheelchair at a facility facing the wall, that's not any kind of longevity we want. We want to be fully engaged in life as we age. And while it looks like through evolution we did a better job, assuming that we didn't get an infection or impaled by a farm implement, at staying rather robust as we aged, diseases of modernity and the sick aging phenotype is a very familiar discussion on this show. And in a moment, we're going to be talking with Dr. Paul Robbins about some breakthroughs that show that maybe it's possible to actually reverse aging. We've talked a lot about aging better, and there's lots of things, therapeutic approaches, diet, intermittent fasting, lots of good stuff out there that shows us how we may be able to age better. But what about actually reversing some of the broken stuff? We're going to be talking about that in just a minute. Of course, I have to thank our title sponsor, All American Pharmaceutical and EFX Sports. Right now, you get 6 of their top-selling products absolutely free by going to superhumanradio.net and clicking one of the EFX Sports banner ads, putting in your name and address in there, and $5 and change for shipping, and you will get 6 of their top-selling products absolutely free, because Dr. Jeff Galini believes that no one should buy anything until they've tried it, and he puts his money where his mouth is. Welcome to the show, Dr. Robbins. How are you?
Just fine, Carl. Thank you for having me.
No, it's very exciting to have you. This is one of my favorite topics because people think that I talk about anti-aging for selfish reasons, and they are selfish, but it's not about looking younger. It's not about buying a Corvette and chasing young girls. It's about staving off age-related disease. Isn't that really the core of the important research today?
And that's correct. I should just point out, though, we view it not necessarily anti-aging, but we're just trying to extend health span. I think trying to reverse aging is going to be more difficult than slowing aging. So as you just said, it's trying to stay healthier for longer, stay out of the wheelchair, stay out of the nursing home, stay out of the emergency room. So that's what we're trying to do. And whether we live longer while doing that, if we extend health span, that's also good. But the goal is to make us age in a healthier way.
And you know, I'm glad you pointed that out, because I did something about 7 or 8 years ago. I stood outside of a Kroger's grocery store, and I polled people, and I asked them, do you believe that you will get a disease in your lifetime? And the great majority of them said yes. So it's almost become the norm to expect disease as opposed to expect health.
That's absolutely true, but obviously we all die from something, and so the key here is to just delay the onset of the inevitable age-related diseases we are going to get, and then have that period of morbidity where we're starting to develop one or more of these age-related diseases to compress that, so we're, again, healthier for longer and sick for a shorter period of time. At least that's the concept that we're trying to do in our approach in the aging field.
So, real kind of a Reader's Digest version of the various theories that have been promoted over the past 100 years or so that have tried to answer why we age in the first place. If you can kind of just give us like the synopsis of where we were, what we looked at, what we figured out isn't it, and now where we are today.
Right, that's a great question. And so obviously aging is much more complicated than any one disease or any type of cancer, for example. But where the field currently is that there are now considered to be 7 or 8 pillars of aging. And these are factors that contribute to driving aging, and these include metabolism, the ability to adapt to stress, just damage to your cells in your body, chronic inflammation, loss of endogenous stem cell function, and then one that we have become very fascinated with more recently, cellular senescence, which is a process where cells, if they acquire damage, stop growing, and then they start sending out danger signals that tell the immune system to get rid of them because they're damaged. And those emergency signals they send out to the immune system are inflammatory factors and actually will stimulate a low level of inflammation and damage the tissues. And there's a lot of evidence now that these damaged cells, these senescent cells, contribute to driving the aging process.
Interesting.
But all of these different pillars contribute, and they're all linked. So stem cells, or adult stem cells, are involved in repairing damaged tissue. They actually become senescent with age, and so they become dysfunctional. And these bad factors, the senescent cells, release into the bloodstream, affect metabolism, and other components of aging. So they're all linked. And so if you improve one of them, you probably would improve the other pillars of aging.
Okay, my first ever interview about cellular senescence happened in around 2007. And it was a study, and I looked for it today, but I couldn't find it. I've changed computers so many times over the years. But the study proposed or promoted the notion that cellular senescence was triggered by glucose signaling. Do you remember any of that sort of stuff? I mean, because diet has an effect on this, as you mentioned a moment ago. But
right.
high fat seems to do it as well. Is there an intersect between glucose signaling and high-fat diets that seem to herald cellular senescence, or is it just the fact of the raw throughput of all of these calories to us, kind of like if you burn 10,000 gallons of gas, your engine is going to be worn out after a while?
Well, they've shown that animals, so mice or other model systems on high-fat diet, develop more senescence, particularly in fat tissue, and this contributes to driving some of the conditions that animals that eat poor nutrition develop. And so if you actually get rid of these damaged cells, the senescent cells, it actually improves metabolism, reduces inflammation, and extends health span. So yes, I think that paper, remember, is one of the first ones that really started to link some of these metabolic phenotypes with age to cellular senescence.
And then people like he was on my show. The guy from England, it'll come to me. Aubrey de Grey, he was a big proponent of the mitochondrial theory of aging, that the more your mitochondria works, the more reactive oxygen species and oxidative stress it puts on the body, you age faster. Have we dispelled that, or is that still kind of a possibility?
We actually just had a manuscript we published last year that strongly supports that model. But again, everything's linked. So if your mitochondria become dysfunctional, they start to make reactive oxygen that then can cause damage to your DNA, that then stimulates pathways that lead to cellular senescence. So mitochondrial dysfunction, oxidative stress, they all lead to increase in the senescent cell burden in the body. So if you use antioxidants, it reduces cellular senescence. Things that improve mitochondrial health also reduce senescence. So again, they're all linked. And so we became interested in cellular senescence because we thought it may be a better target than some of the other pillars or pathways that we're discussing, that we can maybe develop approaches to target them with drugs.
Well, and your approach actually makes sense from a therapeutic standpoint, and that's because regardless of where we are getting cellular senescence from, you have targeted the actual senescent cell. And you're saying, look, we're not going to split hairs about why this happens, but we do know that if we can either remove them or reverse them, the downstream effect is a very positive one. So let everybody else postulate and fight why it happens. We're just going to focus on the cell itself and say, look, now there's some research out there that I've seen, and I think your person in the media department sent along to me as well, that shows that when they transplanted senescent cells into rodents, the rodents really started to age and show the signs of aging. Isn't that correct?
Yeah, so there was actually really two sets or three sets of experiments that changed the view of the role of senescent cells in aging. And the first was actually making transgenic mice so that you could, using a genetic trick, eliminate senescent cells as they accumulate with aging. And if you did that, mice age in a healthier manner. So if you got rid of the cells, that it improved the health span and in some cases the lifespan. The second was developing drugs that actually would do the same thing as a genetic trick. So using drugs that we've identified that will actually kill these damaged senescent cells. And then the third is what you just referred to, was if you inject senescent cells that you generate in the laboratory into a mouse or a rat, this will drive frailty, it will drive metabolic disease, it will drive signs of accelerated aging. So this shows that these damaged cells really are a driving force for aging, not just a consequence, but they actually drive the aging process.
But have we seen the reverse? Have you taken aged rodents and either put non-senescent cells in them?
Right.
And do those then proliferate and kind of level the playing field inside the body?
I think to say that we've actually reversed aging is always a difficult thing. I think we've shown is that it slows the rate of aging, and you might see improvement in certain tissues. And I think the reason why is there has been several published reports, and we have data very similar, that if you eliminate senescent cells or reduce the senescent cell burden, it improves the endogenous stem cell function. So one of the reasons why stem cells become dysfunctional with age is because either they become senescent, some of them, or senescent cells near the stem cells releasing these bad factors lead to stem cell dysfunction. So if you improve endogenous stem cell function, then they can repair damaged tissues more effectively. And so there may be certain age-related conditions that are improved, not just slowed, but improved by eliminating senescent cells.
I'm not a scientist, but whenever I think about this, and I think about it often, because I am 60 years old now, and I do want to live a long time, and I want to be healthy for that period of time, and I know I'm going to die. But when we look at some of the function, hyperfunction, malfunction approaches to aging, to try to explain aging, it almost seems like in order for us to really reverse aging, we have to do two things that are diametrically opposed to each other. The first that you've described so eloquently, but the other one would be to kind of turn on neonatal genes that are responsible for the exact opposite of what we're striving for on one side of the table, to get them to actually open up the blueprints and go, oh, here's how we rebuild that. Is there a yin and yang here ultimately someday, years ahead of us?
Yeah, well, I think we have a long way to go. I guess the best example of what you're talking about is there's technology that's been developed that you can take any cell in the body and revert it to a stem cell, or a type of cell that's assumed to be similar to a stem cell. And you can do that with just activating 3 or 4 genes in the cell. Will now revert it from a differentiated cell, like a skin cell, into a stem cell. And through a genetic trick, they showed if you partially reprogram cells in an older mouse to be more like stem cells, that it actually kind of reset the aging clock. Now, this approach in mice is not something that's going to be applied to humans, but it does show if you can reset the clock and turn on younger genes, that it can have a benefit. The problem is always that there could be an adverse effect. So right. In addition to making us a little bit younger, it actually increases the risk of cancer. So these are things we have to look at very carefully. And what we're doing now in animal models is not ready for prime time in people. But having said that, the approach that a number of people are taking, including my lab, is instead of trying to reprogram or make the stem cells in the mouse or human more effective, we actually are taking young stem cells and introducing them either with or without drugs that can kill these senescent cells. And that, too, seems to have a dramatic effect on slowing aging, and potentially even reversing certain aspects of aging. So I think it's going to be a cocktail of approaches that will be needed going forward. There's really no one approach that's going to change everything, but it's going to be a cocktail that many different types of drugs that target all these different pillars of aging.
Can you, before we go into our first commercial break, can you touch on, I did my first show on transfusing blood from young to old, actually 3 years ago, the first time we talked about it, and whether or not this Nosferatu had the right idea approach actually is meaningful in the research, or is it just too macabre where most clinicians are like, we're just not going to go there?
Well, there actually are clinical trials currently ongoing, and there are companies that are selling young plasma if you want to purchase it. But the data is fairly remarkable. What it shows is that there's something in young serum, there are factors which are still poorly defined, that can slow aging in an older animal. And if you take the same plasma from an older animal and put it into a younger animal, there are factors that stimulate aging. So what you have is you have this balance of good factors in the young serum, bad factors in the old that modulate aging. And so the billion-dollar question is going to be, what are these factors? It's probably not a single factor. It's got to be multiple factors that either drive or slow aging. And so their clinical trials have started at Stanford. Tony Weiss-Corey, who's been a leader in this field for a while, Tom Brando, they are treating at least a certain stage Alzheimer's patients with young plasma because they've shown in mouse models this improves cognition in older animals. So they have started these trials. The FDA has no issues with them because people do blood transfusions all the time.
Right.
So it's not regulated because it's a standard procedure. So they're using plasma, most likely from Stanford medical students or young individuals over 18, to see if they can slow the progression of Alzheimer's disease. And the data from their phase 1 trial some has been reported. I think there's some things that look promising, some things they have to look at in more detail. But this approach is getting a lot of publicity. Clearly, young plasma is not going to be the approach to treat millions of people to keep them healthier for longer. But the important point is going to be to identify what these factors are.
Right.
And that's where everybody's putting a lot of focus, both companies and academia, because that would make a huge difference to human aging if we could identify what these factors are.
I want to take our first commercial break. When we come back, before we dive directly into your research, I want to introduce the role of the immune system, because whenever I hear these kinds of stories, like for instance, several years ago I did an interview where they showed that old and young rodents, they received an injury to a muscle. The young rodents naturally healed quickly. The old rodents didn't. But then they gave some other old rodents oxytocin, and they aged just like young rodents. And then I did a show shortly thereafter that showed that oxytocin increases a microbe in the gut called L. reuteri, which is associated with better aging in rodents and they think in humans. And I started to understand that there's this kind of symbiotic relationship between the outside and the inside of our gut, and the hormones and different things in our blood may play a role in the proliferation and protection of certain things in our gut. And that we're talking about the immune system. Whenever we talk about the gut, I have to remind everybody, hey, we're talking about the immune system when we talk about the gut. I want to just have your opinion on that discussion, and then we'll delve into your research directly, okay?
Sounds great, Carl.
Okay.
Thank you very much.
Sit tight. We'll be right back with more Superhuman Radio. Welcome back. We're talking with Dr. Paul Robbins from University of Minnesota about some emerging research on, improving health span by focusing on what happens as we age. So going into the break, I did this whole connect the dots thing that happened for me over the past several years, where I started to look at the immune system either as a willing participant or possibly the beginning of many of the changes that occur in aging, especially when I started to see research coming out that showed certain hormone levels affected certain gut microbes that are affiliated with immune function and aging slash kind of aging better. What's going on with all that? Is it where's the cart, where's the horse in that relationship?
Well, I think there's still a lot of questions to be asked about the role of the microbiome, which probably plays a very important role, but we're not quite sure exactly how that regulates aging. But I think the role of the immune system in driving aging, systemic aging, including leading to an increase in susceptibility to infection and cancer, the immune system aging probably plays a larger role in aging than we've appreciated. We and others have now shown that if you take aged immune cells or aged immune systems specifically, it seems to lead to systemic aging. And the reason why we think this is true is that immune cells become senescent as you get older. And so your T cells and B cells and other immune cells become senescent, release these bad factors, and because they're circulating throughout the body, they go everywhere and can release these bad factors. And so they contribute dramatically to the aging process. And then the flip side is that if we're young and we acquire these damaged cells, it's our immune system that clears them, because that's what this whole process of senescence has evolved for, is to get rid of damaged cells, and then your immune system comes in and clears them. But as we get older and our immune system starts to fail, it doesn't clear the cells as well. So we have kind of a two-edged sword. They're not cleared as quickly, and that these cells also drive senescence. So we think the immune system is going to be a very important target for drug development, and many of the same approaches being developed to stimulate the immune system to fight cancer could also be done to try to eliminate these senescent cells and improve immune function.
And I want to go on the record. I've said this before. I'm starting to realize that the majority of diseases of modernity are in some way, shape, or form associated with the immune system. Every day, we have new connections between the development of Parkinson's disease and autoimmunity. Now glaucoma has been attributed to autoimmunity. I know heart disease is the number one killer in America today, but I am not convinced that heart disease doesn't occur also from some form of autoimmunity. And when we really look at it, 76% of Americans claim to have gut issues. The rate of distended stomach, SIBO is now being taken seriously by Anthem and other big insurance companies because they realize that if they leave it and ignore it, these people tend to get sicker faster. I keep coming back to, I keep thinking to myself, my God, the term hypochondriac was coined by Hippocrates, and it loosely means below the rib cage. These people had symptoms that couldn't be explained and pinpointed, but they just kind of felt it. And Hippocrates said it's happening in the gut, and that's what that term means, hypochondriac. And I'm starting to come to the realization that if we can fix the immune system and the gut, we may be able to eradicate a lot of these diseases. Now, that's my own little statement. I have no medical degree and nothing anybody can, medical licensure board can take away from me, but that's what I believe. Let's talk about your study specifically. Talk about the design of your study.
Right. So what we did, and this is started in collaboration with the Mayo Clinic, with Jim Kirkland, who's a leader in the aging field and also leader in cellular senescence and understanding its role in driving aging. But we set out to see if we could identify drugs, in particular FDA-approved drugs that could be repurposed to actually kill these damaged senescent cells specifically. And so we developed approaches to be able to screen drugs in the laboratory for those which might preferentially kill these damaged senescent cells and not a normal healthy cell. And what was interesting that during the course of these experiments, we started to realize that these damaged senescent cells are very similar to tumor cells because they've acquired damage, and in theory they should be dying because they're so damaged, but they don't. Mm-hmm. And it's because, like tumor cells, they've upregulated or have higher levels of things that prevent them from dying. And so drugs have been used in the clinic to kill tumor cells appear, at least some of them, appear to be very effective at killing these damaged senescent cells. And which makes sense because what cellular senescence is supposed to be doing, it was actually developed through evolution to prevent cancer. So if you had a mutation in the cell that stimulated that cell to start growing in an uncontrolled way, this pathway to stimulate a senescent phenotype is stimulated to stop tumor growth, and then to release these emergency signals to tell the immune system to clear it. So that's how we would get rid of precancerous cells. And so the senescent process is actually probably there to reduce the risk of cancer. And so drugs that kill these pre-senescent or I should say precancerous cells, those drugs also appear to kill senescent cells. So the first thing that we showed is that a drug called dasatinib that's used for many different types of cancers, but in particular certain types of lymphomas, that this drug in combination with another compound would kill these damaged senescent cells just like a tumor cell. And if you treated mice with these, even mice that were already 2 years of age, which would be roughly our age, Carl, around 60, if you started treating at that age intermittently to clear these damaged cells, the mice were now healthier and they lived longer, and they had fewer senescent cells. So this was very exciting, but it turns out that this combination of drugs is probably not the only combination that will kill senescent cells. And so other clinically used anti-cancer drugs that are supposed to kill tumor cells specifically also appear to be able to kill at least certain types of senescent cells. And so the first clinical trial, or I should say clinical trials for these combinations have started, not for aging per se, but to look at age-related diseases where we know senescence plays a key role in driving the pathology associated with disease, such as pulmonary fibrosis, chronic kidney disease, even osteoarthritis, are all conditions that are now being treated with these, or at least in phase 1 or phase 2, treated with drugs that kill the senescent cells to see if we can reduce disease pathology.
So does dasatinib selectively hit these cells and leave healthy cells alone, or is just the relative fallout to a healthy, robust cell just isn't that bad?
They probably have effects on the healthy cell, but the fallout isn't as bad because they don't have all these damage pathways activated, and then these pathways to prevent that cell from dying because of these damaged pathways from being activated. And the beauty of it, I mean, the beauty of using these drugs that kill senescent cells is they don't have to be given chronically. So for cancer, people take dasatinib chronically for a long period of time because one tumor cell can start proliferating again. But what we're trying to do is just reduce the senescent cell burden, and it probably takes weeks, if not months, for the senescent cells to come back. So the theory is you would give these treatments once a month, maybe even once every 6 months, and that would reduce the senescent cell burden without having any long-term toxic effects on the normal cells. At least that's the concept that we're trying to take forward into the clinic.
And that makes perfect sense. That really does. Yeah. But okay, talk about the role of quercetin as part of this cocktail, because quercetin, while people think it's a really good antioxidant, the two interesting things about quercetin that I learned many years ago is that they seem to affect sirtuins to a small degree, but more importantly, it seems to reduce IGF-1 conversion from growth hormone, doesn't it?
Yeah, so quercetin does a lot of different things, and so the problem with using it is you don't know what its specific target is. We chose it because it was shown one of its activities, one of its many activities, was targeting a specific component that appear to be upregulated in these senescent cells, just like tumor cells. And we've shown if you combine quercetin with dasatinib, that combination was seen to be more effective at causing death in at least certain types of senescent cells. And it appears in mice, at least, that this combination is more effective at clearing senescent cells. Why or how quercetin is doing this is still not quite clear because it has so many different targets. But having said that, we've now shown that other related compounds, not quercetin, but ones that are very similar, probably work even better. And then we can do medicinal chemistry and make them even better than that. So we think the quercetin, although good, can be improved upon tremendously. And we think dasatinib is just one of many anti-cancer drugs which also will be able to lead to death of the senescent cells, at least of certain types. And I should point out, I'm talking about senescence, and there's probably different types of senescence, and probably different tissues have different types of senescent cells. So it's not like it's just one type of cell. There's probably a variety of types of senescence, and that's what the field is now looking into more detail, is really what are the key types of senescent cells that drive aging, where are they, what tissues, such as the immune system, and then can we identify drugs that target this specific subset that seems to be important at driving aging.
So you said there are other agents besides, you say, I say quercetin. I got a Brooklyn accent. I'm stuck with it. But anyway, how about the gingerol families found in ginger? They several good studies on cancer and its effect, gingerol's effects, especially the 6 and the 8 forms. It shows that it reestablishes the apoptotic landscape and cancer cells just die on their own. And it also is inhibitory to cyclooxygenase, so it has an effect on inflammation. Would that be also a good choice with the dasatinib?
It's something that just you described that it could work. I'm not aware of anybody. We've not looked at it, but I'm not aware of anybody else who's looked at it in combination. But the rationale for it makes perfect sense. And so what we're doing, and we're trying to do kind of rational design, rational thought for identifying compounds which might work synergistically with either dasatinib or quercetin, or we have published that things targeting a heat shock protein or a chaperone protein that helps proteins fold, HSP90, if you block its activity, that leads to preferential death of senescent cells. And then also there are a number of anti-cancer drugs that target what's known as the BCL2 family proteins, and these are proteins which are known to prevent cells from dying, and they're expressed much higher levels in tumor cells. And that class of drugs has been shown to be very effective. And it's actually that class of drugs that target BCL2 that's in the clinic for osteoarthritis.
Yeah, because we now know osteoarthritis also has its beginnings in autoimmunity now. It was always thought that just rheumatoid arthritis and things like psoriatic arthritis were autoimmune disorders. But now we realize that relatively lean people whose joints don't experience a lot of mechanical loading have inflammation that destroys chondrocytes, and they've even attributed that. They say, hey, that osteoarthritis actually finds its beginnings in autoimmunity. Isn't that right?
Well, there are a number of reports that say that there's an autoimmune component to osteoarthritis, like rheumatoid arthritis, but the data that's coming out in regard to senescence in osteoarthritis is that if you look in the cartilage of individuals with osteoarthritis, there are a large percent of those cells which are senescent. And if you clear those senescent cells, again, using one of these drugs, the senolytic drugs I've been discussing, that improves pathology, at least in animal models of osteoarthritis. And so one of the problems of senescent cells is they release an inflammatory cytokine called IL-1. And IL-1 is probably a key driver of cartilage destruction. So a number of drug companies have been trying to develop things that target IL-1 because it is what leads to degradation of cartilage. And senescent cells, which appears the chondrocytes can become senescent, which may be because of the weight, just mechanical stress, maybe a variety of factors, that those senescent cells that arise because of the stress release IL-1 that leads to cartilage destruction.
Interesting. I want to take our next commercial break, and when we come back, I want to come back around and talk about the immune system and some of the research that's being done on the anti-rejection drug that's given to people who have had organ transplants, but obviously they take it chronically ongoing for the rest of their lives. But there seems to be some benefit from intermittent exposure to rapamycin. And I'd like you to talk about that in our next discussion, okay?
Sounds great.
All right, stay tuned. We'll be right back with more Superhuman Radio. Many of you know that my approach to science changed in 2014 when I had Dr. Daniel Lieberman on the show, and we talked about his amazing book, The Story of the Human Body. Every scientist, every layperson, every person should read it to understand the trajectory of humans throughout evolution and why we have the things we have that are gifts and why modernity seems to challenge them. If you haven't had a chance to read the book, and every time I talk about it, you go, I got to get that book. I got to read it. I have an opportunity for you to literally absorb all of the salient information in that book in 15 minutes. You've heard me talk about an interesting new app that I discovered recently, and I've talked about it because I keep telling people you've got to get on the program. It's called Blinkist. Blinkist reduces entire books to a 15-minute audio of blinks, and they break everything into segments, and they give you all of the important takeaway information from a book in 15 minutes. In your commute, your drive, you're on the treadmill doing your cardio, whatever it is, you can absorb all the information, and they have over 2,500 nonfiction books to choose from. And guess what one of them is? It's The Story of the Human Body. If you go to Blinkist.com/superhuman, you'll get a 7-day free trial. And I'm telling you, your brain will thank you. So don't put it off another minute. Check it out. We're talking today about wonderful anti-aging approaches. So what do you think? What do you think about the this emerging information about anti-rejection drugs that seem to just shut the immune system off for 1 day every 2 weeks and promise to help us eradicate some of the diseases of aging?
Yes, so the compound you're talking about, the drug is called rapamycin, which has been used to suppress the immune system in transplant individuals, transplant recipients. But the dose they use of the rapamycin is much higher than what has been shown to extend lifespan, at least in lower vertebrate systems. So it's been shown in mouse models that if you put them on rapamycin starting either early in life or even now older in life, that it will lead to a life extension and a healthier lifespan in both male and female mice, which is important because many drugs which have been shown to have effects, at least in mice, affect either males or females, but not necessarily both, which is an interesting observation. But rapamycin has been shown to affect both. And so it's now being tested more in the laboratory, but also in the clinic, giving it either intermittently or for a short-term period to see if you can improve with certain conditions. And I think the best example was published last year from Novartis, where they tried to determine if treating the elderly with rapamycin for a short period of time would improve their immune function, not suppress it, but improve it, leading to a better response to the flu vaccine. So they put people in their 80s on rapamycin for a period of time, took them off, gave them the flu vaccine, and showed they had a much better immune response to the vaccine than age-matched controls that were not given rapamycin. So this is very exciting. And so they're now trying to figure out exactly how to give it, how long, when to start, to see if you can ameliorate other age-related conditions in humans. And another exciting observation that was made, or I shouldn't say observation, but clinical study, is started at the University of Washington, where they are now treating dogs with rapamycin to see if it will extend the lifespan or health span of canines. And the rationale is unlike laboratory animals that aren't in the same environment as humans, dogs share a house, share many of the same environmental cues as humans. And so the question is, if you put them on drugs like rapamycin, will they see an improvement that could be similar to what their owners would see if they were taking rapamycin? So they're now doing a rapamycin trial to see if it improves health span and lifespan in pets, in dogs, which is a very interesting approach, and I think the initial data is looking very promising.
Okay, so let's talk about the immune system for a second. You corrected me when I said it suppresses the immune system.
No, that's true. At high doses, that's the reason it's given to the transplant recipients. It suppresses the T and B cell responses. So that is absolutely true.
But in this approach, isn't it still suppressing the Th2 immune system, the acquired immune system? Because isn't the whole problem with flu vaccines and a lot of these other things that they stimulate antigens, but the Th1 portion of the immune system really doesn't get activated, so it's not truly embedded in the immune response. And when we look at some of the things that we're seeing today with immune systems going awry, where they're attacking thyroid tissue or chondrocytes and stuff like that, isn't this just in lay people's terms? I mean, I'm just an average guy, but just an imbalance in the innate versus the learned immune system, and rapamycin seems to kind of go, hey, everybody, let's get along. Let's just calm down for a second.
Well, so the enzyme it targets, which is it actually was named the mammalian target of rapamycin because that's how it was identified as the target for this drug, regulates a number of cellular processes. It regulates the cell's response to amino acids, the nutrients, to a variety of environmental cues that stimulate a cell to grow or to stop growing. And so if you use this drug, it does a variety of things. And it depends also on the dose and how frequently you give it. So it does kind of reset the immune system. But it also improves the aging immune system because it's been shown that it actually reduces things that go wrong in senescent cells. So if you treat a senescent cell with rapamycin, many of the things that a senescent cell does goes away. It doesn't release these inflammatory factors. It doesn't release these emergency signals. So it actually has been shown to suppress senescence. It doesn't kill the cell, but it actually suppresses these cues. So one hypothesis is that what rapamycin is doing is that it's reducing senescence in the immune system, but also in other tissues. So that's one potential mechanism. There's probably about 5 others, 10 others. So it's a very complicated process, but it depends on the dose, how often you give it, what age you give it. And so it's very exciting. There are trials now ongoing for Parkinson's, for Alzheimer's, because there's been very good preclinical data using rapamycin in that setting. And then rapamycin has a few side effects. So a number of companies are putting effort in developing what are called rapalogs, which are similar compounds that may not have the side effects. So rapamycin has been shown, if given at high dose, to cause testicular atrophy, which is not something that aging males would want to have. So they're trying to see if they can find things which are a little bit safer. It's also been known rapamycin has adverse effects on beta cells, so it can affect your metabolism. And so they're trying to find these beta cells in your islets that release insulin. And so they're trying to find versions that maybe don't have this adverse effect on beta cells. So and some of these new rapalogs are now in the clinic for a number of different conditions, including cancer.
But okay, so those of us who are avid weightlifters, which this audience is made of, we know the importance of mTOR1 and mTOR2, 1C, and so on, because it stimulates protein synthetic response. It's acted upon not only by muscular loading, but also nutrient amino acids like leucine. So when we talk about mTOR in the context of cellular senescence, does that mean that those of us who tend to work hard to maintain the amount of lean body mass we have as we age are doing ourselves an injustice?
It's a great question. I would say not. I would say that mTOR does a lot of very good things. It does some things that if it's too elevated may not be good. So there's no evidence that exercise is bad for you in any way. In fact, all health studies show that exercise, including weightlifting, again, maybe not to the extreme, but within reason, that it's very beneficial, reduces senescence, extends health span, and improves memory, improves cognitive function. It does a variety of things. So muscle mass is extremely important. So it's just mTOR regulates more than just protein synthesis and cell size. It regulates a variety of other things in response to signals. And so I guess one example would be is that one thing that's known to lead to extension of lifespan, at least in mice and other model systems, is caloric restriction. And that's partially thought to be due to limiting specific amino acid uptakes, which regulates presumably mTOR. So caloric restriction, maybe eliminating certain amino acids from your diet, they all seem to have effect on mTOR activity, and so that's probably at least one of the mechanisms through which caloric restriction has had this benefit. The problem with caloric restriction is not all species respond in a positive way to it. So if you take 20 different mouse strains, a few of them will respond well to caloric restriction and live longer. Some of them will actually live shorter. So that's the problem with the field, is trying to figure out who's going to respond well to a certain drug or a certain nutrient intake or reducing caloric intake. Because even in animals such as a mouse or a rat, there's huge differences between strains, and which makes this all very complicated.
Right, and humans too. Okay, so one of the things that has come about in the past 5 years now, it started back in Dr. Stu Phillips's lab up at McMaster's, is that perhaps caloric restriction isn't as necessary if we. I hate the term intermittent fasting. I like to say a more ancestral feeding pattern. You know, before we had refrigerators and cupboards, and maybe even before we had modern agriculture going back past 40,000 years, we ate probably not first thing in the morning. We usually had to go out and find food. And even Dr. Malin Watfie's book of Doves, Diplomats, and Diabetes seems to illustrate this in today's diobese model. So we are learning now that you can actually, by timing, having a smaller feeding window, a larger fasting window, you can actually stimulate a lot of the same metabolic mechanisms that we see in caloric restriction, but without actually starving yourself. And we also learned 2 years ago, I did a show that showed that the role of basal autophagy plays an amazing part in protein synthesis, that in fact, stimulating autophagy, which generally only occurs when you're not eating, it actually promotes muscle growth to a greater degree when you give an isocaloric diet to two groups of trainees that are working out. And one group is breaking their meals up into more frequent and the other group is just eating 3 times a day. Those periods of autophagy actually help stimulate protein synthetic response by cleaning up the waste products from the workout. So it's starting to play out now that, maybe we don't have to starve ourselves. We just don't have to eat so frequently. And the other interesting thing about fasting is it also seems to have a direct effect on kind of quieting the immune system.
Absolutely true. And so what's interesting when you talk to scientists in the aging field about what regimens they follow, what do they eat, how often do they eat, you realize that there's nobody believes in only one approach. I know scientists that are really limiting calories, other ones who only eat for a 5-hour window during the day. They say, I don't care what I eat as long as I eat it only in the 5-hour window. And so you get this whole spectrum. Some people taking resveratrol, some people taking an NAD precursor, some people now trying to take a drug that they think acts as a senolytic to kill the senescent cell. So it's really interesting about what the different approaches that scientists who study this are taking, and you realize there's no consensus. But having said that, there were 2 studies done in primates that look at caloric restriction. One that showed caloric restriction extended lifespan, another one said there was no effect. And when they compared data, they decided that the reason why there was a difference is because it wasn't the caloric intake, it was how long during the day the monkeys were eating. Some monkeys were able to eat all day long, but have a lower caloric intake. The other set, they took the food away, so they can only eat for a short period of time, and that was just kind of how the study was designed. And it turned out it was the ones that were eating over a short period of time, it was those monkeys that actually lived longer and healthier. So I do think that limiting the time during the day that you eat is going to be very important, as you said, because that's how we probably evolved.
Yeah. And, and again, that's why I'm such a huge fan of evolution. I get people ask me questions, and before I answer them, I think about evolution and why would we have this? Why would this be a phenomenon? Is this a gift? And we have just abused it, and so now it's turning into a deficit. When we look at things through evolutionary science, we go, oh, now I get it. I see what's going on here. And it's really amazing. So in summary, the research that's being done right now on the dasatinib and other agents that could coincide, like quercetin, this is actually being done with humans now, you said?
There are phase 1 and phase 2 trials, depending on the indication, that are ongoing, small trials to see if there's a short-term benefit, which then hopefully will lead to additional studies and eventually try to see if we can slow aging.
Very exciting.
First is really to document that these drugs will clear senescent cells from a person that has a high senescent cell burden, such as those that may have had whole body irradiation for cancer or high-dose chemotherapy because of their cancer, to see if we can clear these cells, and if yes, then the trials will extend longer and see if we can actually slow aging. But yes, there are trials currently underway.
And the thing that quercetin contributes to this, you said it actually suppresses the production of something that senescent cells produce that seems to cause a lot of problems?
Well, it targets something called PI3 kinase, a certain isoform of this. But we don't know if that is the important target, or it could be actually the antioxidant activity in the mitochondria could be the activity. So that's been the problem with quercetin because it has so many activities.
Right.
I can't tell you what it's targeting.
Okay.
Dasatinib targets kind of a spectrum of tyrosine kinases, so I know that they are important. At least one of them is probably important. And so there's more specificity. Quercetin does a lot of different things.
Okay. Listen, I want to thank you so much for being on the show today, Dr. Robbins. This is fascinating, and I hope that that we can keep in touch with you as new information arises. We can get you back on the show.
Carl, I really enjoyed it. I really enjoyed talking with you, and yes, I would love to come back.
Great. Take care.
All right. Take care.
We're going to take one quick commercial break, and when we come back, I got to clear something up about a show that I did last week about we were talking about the ketogenic diet, and we ended up stumbling on sugar alcohols and if they possibly actually convert to sugar. And during that interview, we gave a blanket, all sugar alcohols seem to convert to sugar. This may not be the case. I want to talk about that when we come back. Stay tuned. Welcome back. So last week we did a show with Patrick Dahlin from Black Belt Nutrition, talking about some things that happen, unique things that happen in the diet as it relates to the ketogenic diet. And one of the things Patrick said during the show that I wasn't prepared for at all was that sugar alcohol turns into sugar. And I stopped him. I made him repeat it. I was like shocked because I had never heard this before. Apparently some of you have heard it before. I had an outpouring of messages from people saying both good and bad, both that this is baloney, it doesn't happen, it's BS, and other people saying I've known it all along and I avoid sugar alcohols for this reason. So I never want to go off half-cocked, you know that. I mean, I've changed my position as I learn new things, and so I started to really look into this. And I'm actually asking Patrick Dahlin to come back in because I asked him to research. So the research that was originally done was in 1966 and 1975. And both of these studies looked at the inhibition of fatty acid oxidation into and also fatty acid conversion into ketones when fed certain sugars and polyalcohols. One of them was sorbitol. And so these are sugar alcohols that are fairly old, that have been around for a long time. And fast forward today, we have a lot of new sugar alcohols. Xylitol is one of them. More importantly, mongrosides that are found in monk fruit tend to be sugar alcohols. And there's plenty of research on monk fruit that shows that it does not cause a rise in blood sugar. Now, I asked Patrick Dahlin to look at the research to see if they also looked at insulin. Because if you raise blood sugar just a tad, but you can produce enough insulin quickly to suppress it, you may not see the spike. I'm not talking about like a big meal. I'm talking about just a little rise. That could be masked. So you have to look at basal glucose, basal insulin. Then the sugar alcohol is introduced. Then you have to look at post-supplementation glucose and post-supplementation insulin. If glucose stays the same but insulin spikes, there's definitely a metabolic change that's happening. The body thinks it's getting sugar. And whether or not that small spike of insulin could actually be the reason for the anti-ketogenic response. But there are new sugar alcohols out there, and one of them that's really relatively new, that was introduced to the sports nutrition industry by Quest, and it's called allulose. And allulose, while I believe it is classified as a sugar alcohol, and I could be wrong about this, and we're going to find out because Patrick Dolan's going to look into all this. Allulose seems to pass through the body relatively undigested, and in fact, almost completely undigested. It comes in through the mouth and it goes out through the anus the same way. That fact that it moves through the body undigested would mean that it can't really have an effect on insulin or glucose because the body is not getting it. It's just passing through. It's like that piece of corn that comes out whole, after you eat corn on the cob. It didn't affect anything. It just rode the train out. That's all it did. So before we put an end to this discussion about what sugar alcohol does on a metabolic level in the body, and if it's anything to be concerned about, we're going to have Patrick Dolan back on and have him dig into some of this research on some of the newer sugar alcohols, because they've gotten more sophisticated. And also, like allulose, they could be some that just are completely undigested. They just pass through. So, I am doing my part to clear up any questions about this because I want to know too. Because I use products that have sugar alcohol in them, and I told Elisa when we started talking about this, she says, "Oh my God, so big deal. Like we also have sugar in our diet, right? There's things that she and I eat that have sugar." We don't avoid sugar completely. Now, granted, it's not a large portion of our diet by any means. It's very small. But if I had to start looking at sugar alcohol the same way I look at sugar, it's not going to stop me from eating the occasional dessert or a protein bar or anything like that. Because I don't avoid sugar completely. It's not like as though I won't buy something because it has sugar in it. I mean, I eat a half a bar of a 90% chocolate product, 90% cocoa chocolate bar that's got almost 4 grams of sugar in a half a bar. I don't not eat it because it's got sugar in it. So we also need to deal with these kind of things in a sensible manner. Nothing in life is all or nothing. So we'll get to the bottom of this. We'll do a follow-up show, and we'll make sure to deliver exactly the right information because it's important to all of us. It's important to me as well. But I wouldn't start avoiding sugar alcohols just yet, especially if you're not on a ketogenic diet, because it looks like the sugar alcohols may suppress ketone production, but that doesn't mean anything if you're not on a ketogenic diet. If you're not looking for ketones, I mean, once I break my fast, I don't care if my body's still producing ketones. I'm not eating 80% fat so I can keep producing ketones. I'm eating foods that are going to spike sugar, vegetables and starches and stuff like that. So the reality is that this discussion shouldn't matter to anybody unless maybe they're battling brain cancer and they seem to be having trouble producing enough ketones. Well, maybe they can look at sugar alcohols and see if it's having any impact on them. I know Andrew Scarborough messaged me and said that in his case, he avoids sugar alcohols because he's concerned about them producing sugar. Glucose in the blood, and he's battling, he never wants his brain tumor to come back. But if you're just an average person who's choosing a protein bar as a snack because it's high protein, and it turns out to have 4 more grams of sugar than you thought because the sugar alcohol impacts you, that's not a big deal. It's really not. And so we have to be sensible. And that's where the zealotry needs to get out of nutrition. The zealotry that dictates that you eat only this way, you eat only that way. I mean, there are some things to avoid, but that's because of modern agriculture and what they're contributing to certain foods in the way of pesticides and so on and so forth. I'm still not a proponent. I still don't believe a little bit of chemicals is okay for you when it comes to herbicides and pesticides. But you know what? if the sugar alcohol turns into sugar a little bit more readily, in my day, it's not going to change anything. I'm not a bodybuilder. I'm not looking to get to single-digit body fat levels. I'm looking to enjoy life while staying healthy. That's it. And that's what most of us are. So don't be afraid of sugar alcohols just yet. The jury's not out on this, especially as it relates to allulose. Because like I said, allulose passes through the body undigested. So it can't have any effect on you. It's like you didn't eat it at all, except the taste. And if if glucose regulation starts at the tongue, well, maybe the body may expect something sweet and squirt a little insulin out, but that's going to just make you hypoglycemic. It's going to lower your blood sugar. Now, that would be an interesting thing because that means that eating a bar with allulose would be good for a diabetic because it would actually have the reverse effect. It would actually lower their blood sugar postprandial as opposed to raising it. How about that? The jury's not out. We'll cover this more. And tomorrow we have a great show. Dr. Jeff Galini has a study that he's going to talk about tomorrow about how long-term adherence to a strict ketogenic diet may actually burn out the pancreas and why. This is really fascinating. This may be why people who are on long-term ketogenic diets seem to stay fat or get fatter. And again, long-term ketogenic diets are no more appropriate for the human than long-term vegan diets. And here's the reason, folks. Vegans have to supplement with different things, B12 and other things, because they don't get it in their diet. And people who are strict ketogenic dieters, they have to supplement with stuff too. They have to find ways to get minerals if they're eating very, very high fat. They have to take vitamins because they're not getting them in their diet. Any diet that requires you to supplement is not appropriate for the human being for any long term. I mean, it could be a couple months because from an evolutionary perspective, you may have found yourself without any greens and having to eat a lot of fat. But usually if you're eating protein and stuff like that, you're getting some of these vitamins through the animal flesh. But if you're on a strict ketogenic diet, you're eating like a lot of fat, you have to supplement with things. That in and of itself shows that it's not appropriate. Because there were no GNCs a million years ago. There were no vitamin shops a million years ago. There's no place for somebody to go, oh, if I'm going to be eating all this fat, I need to find minerals. Where can I get some minerals from? So most likely a long-term ketogenic diet would have led to nutrient deficiencies that could have either shortened or ended lives or caused disease states in offspring. So once we start becoming zealots about diet, oh, this is the only way to eat, that's where we lose it. We really is. I will see you tomorrow with more Superhuman Radio. Thanks for listening today.